Okay, next exercise 55. Let G be the symmetry group of a circle. Show that G has elements of finite order as well as elements of infinite order. Okay. Let R1, R2 be counterclockwise rotations. So we have to show that elements of both the types are there in G. So one example of each type is enough. So let this be counterclockwise rotations about the center of the circle through angles 180 degree and say square root of 2 degree respectively. Now they are rotations, counterclockwise rotations through some angles where the center of rotation in each case is the center of the circle. So when you perform such a rotation, after performing the rotation, the circle looks the same. So each one of them is a symmetry of the circle. So they both will belong to G. Clearly, R1 and R2 belong to G. Now because R1 is rotation through 180 degree, R1 itself is not the identity. But if we perform R1 two times, then the points of the circle are mapped onto themselves. That is, it's like this. This is the circle. Points are mapped onto, say this point will come to this point. So they get the diametrically opposite position. But if you do that two times, all the points will come back to their original position. So performing R twice is the same as doing nothing. So that is why R1. So R1 square is identity. Note that so since R1 itself is not identity but R1 square is identity, so the order of R1 is 2. So R1 is an element in G of finite order, and the order of R2 is infinite. Why is the order of R2 infinite? Actually, I want to end the solution here itself, but let me just tell you how one can show that R2 is of infinite order. Suppose R2 has finite order and let the order be some positive integer n. Then the nth power of R2 should be equal to the identity. Now since we are performing rotation, the rotation R2 n times. So after performing, the angle that you will have, that you have rotated through that angle is equal to n times root 2 degree. Now if this has to become the identity, then it should be the same as some integer multiple of 360 degrees, a full rotation for some positive integer n. Now this implies, neglecting the unit degree of course, this implies this, which says that since the right hand side is a ratio of two integers, is a quotient of two integers, so square root of 2 is rational, which we know is not true. We already know that square root of 2 is an irrational number. So there you get a contradiction. So your supposition is wrong and hence R2 must be of infinite order. Next, exercise 56. Let X belong to a group and the order of X be 6. Find the order of X square, the order of X cube, that of X to the power 4, and order of X to the power 5. Just like that, let Y belong to a group and the order of Y be 9. Find the order of Y to the power I for these choices for I. Okay, and lastly, do these examples suggest any relationship between the order of the power of an element and the order of the element. Okay. Now to find the order of X square and the order of X cube, we can directly use the result we saw in exercise 51. Namely that if A is a group element of order n and D is a positive divisor of n, then the order of A to the power D is n divided by D. This we can use only for the case x square and x cube, but for the other cases we of course have to devise something else. We have to argue differently. By exercise 51, this is 3, and like that order of x cube will be 2. Okay. Now to find the order of x to the power 4, we have to of course look at the powers of x to the power 4. The first positive integral power that becomes identity gives us the order, that is its corresponding exponent will be the order. Since order of x is 6, we have x to the power 4 not equal to the identity element. So that we know, we can begin like that. Now what happens if the second power of x to the power 4 becomes equal to the identity? Then x squared, that can be written as x to the power 8 times x to the power minus 6 by the rules of exponent, is equal to identity. This becomes identity from the hypothesis. This is identity from the given condition. So that is also a hypothesis. I mean, in this implication, this hypothesis gives us identity for x to the power 8, and our original hypothesis gives us identity for x to the power 6. So this is identity and this is a contradiction. Why is it a contradiction? It's because since order of x is given to be 6, so x square cannot be equal to identity. So that thing is contradicted. So that means x to the power 8 cannot be equal to identity. And what about the third power? This becomes equal to the identity. So order of x to the power 4 is 3. Next, we are going to show that the order of x to the power 5 is 6, since this is equal to 6, x to the power 5 itself is not equal to the identity. If is equal to the identity, then x to the power 4, which is this, is also equal to the identity, a contradiction. again a contradiction. Okay, so the third power is also not equal to the identity. When t is equal to the identity, then because 6 times 3 is 18 and x to the power 6 is identity, so this becomes identity and this is identity from our hypothesis. Again a contradiction. Then if the fifth power is the identity, then (25) times x to the power minus 24. 4 times 6 is 24. So this becomes identity. Again a contradiction. And lastly, so order of x to the power 5 is equal to 6. Now we have to find the orders of these powers of y. Next, one of them of course can be found like this using exercise 51. But unfortunately that is only one case. Order of y cube is order of y, which is 9, divided by 3. So this is equal to 3. Okay, since order of y is, okay, now we are going to find the order of y square. Order of y is equal to 9. So y square itself is not equal to the identity. If y square whole square, which is y to the power 4, is the identity, then y to the power 5, which can be written as y to the power 9 times y to the power minus 4, it becomes the identity, a contradiction. Contradiction to this statement, this hypothesis that the order of y is 9. Okay, then if so this is the second power, then what about the third power? Oh, I think okay, hold on. This is already not equal to identity. So we can write like this: y square is not identity, its square is also not identity because 4 is less than 9. Then the cube is also not identity. Y to the power 6. that is also, this is 6, also not equal to identity, 6 being less than 9, and we can argue like this for one more power. 8 is not equal to identity. Okay, so now we can look at the higher powers. If equal to by to the power 10, if this becomes identity, then this is identity, a contradiction. If then y cube, which is y to the power 12 times y to the power minus 9 is identity, again a contradiction. If y square whole to the power 7, which is y to the power 14, is identity, then y to the power 5 again a contradiction. Okay, so two more powers are left, the 8th power and finally the 9th power. If this is equal to identity, again not possible, because 7 is less than 9. And finally, this is equal to identity. So order of y square is 9. Similarly, one can prove, I am not going to of course calculate all the other things, one can prove these things. Similarly, one can calculate this also turns out to be equal to 9, that also turns out to be equal to 9. However, the order of y to the power 6 that will be equal to 3 actually. Let me see if that is the case. Yes. This will also be 9 and this will also be 9. Okay, so now we have to make a conjecture or a guess. We have to guess the relationship between the order of y and an integral, positive integral power of y, or for that matter the order of any element and the order of a positive integral power of that element. From the above examples, we conjecture the okay, this is not, this doesn't sound right. We make the following conjecture. If A is a group element such that order of A is equal to n, then for any integer okay, let me just wrap this up and then we will see. Then for any integer I lying between two and okay, we haven't exceeded the order. I mean, the exponents we have considered here did not exceed the order. In case of x, the exponents were 2, 3, 4 and 5, where originally the order of x is given to be 6. In case of y, the exponents vary like this and the original order is 9. So that means n minus 1, the order of y to the power, we are considering n, so order of a to the power I will be equal to, let us see the cases. This we found to be 3. This is 2. This one is I think it was 2, or what was it? I forgot. 3, 3. And this was 6. So looking at it, we see one thing, that the order is the order of x divided by the greatest common divisor of the exponent I and the order of x. You see, this is 6 divided by 2. The GCD of 2 and 6 is 2. These are special cases, of course, because in this case the exponent itself divides the order. The GCD of 3 and 6 is 3. What about this one? 6 divided by 2. The GCD of 4 and 6 is 2. This one is 6 divided by 1. The GCD of 5 and 6 is 1. Is this also the case for the powers of y and their order? Let's see. Order of y square is 9. The GCD of 2 and 9 is 1. So dividing 9 by 1 we get 9. The order of, okay, we have them here. Y to the power 4 is also 9 because the GCD of 4 and 9 is again 1. And just like that, the GCD of 5 and 9 is also 1. So dividing 9 by that we get 9. Okay, now the greatest common divisor of 6 and 9 is 3. So that's why 9 divided by 3 is 3. Then after that, the GCD of 7 and 9 is 1. So here we are getting 9. Again the GCD of 8 and 9 is 1. So again we are getting 9. So our conjecture is this. Order of A, which is n, divided by the greatest common divisor of I and n. This is our conjecture, which of course it is a conjecture because we are not going to prove it. We are just guessing that this is the case based on these examples. Then D4, the dihedral group D4 has 7 cyclic subgroups. List them. So to find the cyclic subgroups, you just have to look at all the elements and the cyclic subgroups they generate. The cyclic subgroups of D4 are, the first one of course is the trivial group consisting of only the identity element and also generated by the identity element. Then the subgroup generated by the rotation R90, which turns out to be equal to the subgroup generated by the rotation R270. You can verify these things. Then the subgroup generated by the rotation R180. Okay, and this is a cyclic subgroup of order 2 because this element is of order 2. So it has only 2 elements, R0, R0 and R180. Then the subgroup generated by the reflection H, that generated by the reflection V, then the one generated by the reflection D, and finally the one generated by the reflection D prime. So 1, 2, 3, 4, 5, 6. Oh, are we getting more than 7? Yes. 1, 2, 3, 4, 5, 6, 7. Okay. Then U15 has 6 cyclic subgroups. List them. I need ink. These are the cyclic subgroups. You can verify. The first one, of course, is the one generated by the identity. Then the subgroup generated by 2. For your convenience, I am also going to write the elements. Then the subgroup generated by 4, which has only 2 elements, 1 and 4. The subgroup generated by 8 turns out to be equal to the subgroup generated by 2. So we don't get anything new. Okay. Then the subgroup generated by 7, which has these elements 1, 4, 7 and 13. Then the one generated by 11, it has only 1 and 11. And finally the one generated by 14, which has only 1 and 14. Any other element, if you take any other element from U15 other than these generators, then that will generate one of these subgroups. Okay, so we don't get anything new. So there are 6 in total, 6 distinct cyclic subgroups. 1, 2, 3, 4, 5, 6. Exercise 59. Prove that a group of even order must have an element of order 2. Okay, let G be a group such that the order of G is 2 times M, where M is a positive integer. Okay. Let G belonging to G be a non-identity element of odd order. It's easy to prove that the order of G inverse is also equal to the order of G. Thus, in G, non-identity elements of odd order come in pairs. Pairs in this sense that one element of that pair is some element and the other is its inverse. So in that way we can form pairs. You consider any other non-identity element, then the order of that element, if the order of the element is odd, then the order of its inverse also should be odd. So what does that mean actually? It means that, see, in G of course we have the identity. So apart from the identity, there are an odd number of non-identity elements, and the ones among them having odd order come in pairs. So that means since they come in pairs, so the elements of odd order, the total number of such elements must be even because they come in pairs. And since this number is odd, so all the non-identity elements cannot have odd order, because together they can produce, the elements of odd order can produce a number that is even, whereas this is odd. So that means there must be a non-identity element whose order is even. Since there are an odd number of non-identity elements in G, there must be a non-identity element A in G whose order is even. Actually there is no need to consider this part, no need to write this separately, but anyway, since we have written, we don't want to change it. Whose order is even. Let the order of A be 2n, where n is a positive integer. Now, since n is strictly less than 2n, this is happening because n is a positive integer and order of A is 2n, we have order of A to the power n, or rather I should write this, not saying order straight away. A to the power n cannot be equal to identity. because 2n is the smallest positive integer for which a to the power 2n will be equal to identity. So the smaller positive integer n cannot give us identity, that is the corresponding power cannot be equal to the identity. Also a to the power n whole square, which is a to the power 2n equal to identity. So the first power of a to the power n is not identity, but the second power is identity. Hence order of a to the power n is 2. So that means in our group G, a to the power n is an element which has order 2. Exercise 60. Suppose G is a group that has exactly 8 elements. Of order 3. How many subgroups of order 3 does G have? Okay, since we don't yet know Lagrange's theorem and those things, so we will have to argue separately. I mean, we cannot use such advanced results here. Let H be any subgroup of G of order 3. Okay, we are now going to show that H is actually a cyclic subgroup. It has to be a cyclic subgroup of G. Since H has order 3, so we can choose a non-identity element in H. Choose A in H minus E. Okay, so A is a non-identity element. Suppose A square is identity. Suppose this is the case. Next, that means what? A is there in H, E is there in H, and A and E are different elements. So besides them, there is one more element in H. So such an element we are going to choose minus E, comma A. Okay. Now we claim that this B, okay, so now, okay, why did I choose B? I mean, of course I want this supposition to be wrong. Let me just think. It came to me and then it went away. I have chosen B to be that element in H which is neither E nor A. Okay, then what is B square? Since H is a subgroup, B square should also belong to H. Since B square belongs to H, we must have B square. Okay, so note that since B square is in H, B square is either E or A or B itself. But B square cannot be equal to B, because in that case, by the cancellation laws, B should be equal to the identity. We have to now write these things systematically. We must have B square equal to E or B square equal to A or B square equal to B. Clearly, B square is not equal to B, since B is not equal to the identity by the cancellation law. Otherwise, we will have B equal to identity. Now, what happens if B square is equal to A? If B square is equal to A, then we already have A square equal to identity. We will then have B to the power 4 equal to identity. Okay. But does that give me anything wrong? If B square is equal to A, then what can possibly go wrong? B to the power 4 becomes identity. Okay, that means, does that give me anything useful? I thought about it, but then or instead of considering B square, I think it will be better to consider B inverse. We must have B inverse equal to identity, or B inverse equal to A, or B inverse equal to B. Okay, clearly B inverse is not equal to identity, since B is not identity. Fine. If B inverse is equal to A, then using this A square equal to E, we have this. Because A square is E, A square is equal to A inverse. Which implies B has to be equal to a contradiction. Because according to our choice, B is not equal to A, and for that matter, according to our choice, B is also not equal to E. See, that's why we have been able to conclude this. So we must have B inverse equal to b. Okay, or b square equal to identity. Now AB also belongs to H because A and B are elements of H, and hence AB is E or AB is A or AB is B. Okay, I think I'm not I'm getting bits and parts of the solution, but I have not been able to write it systematically. Things are going in this and that direction. So what I'm trying to see here is I want to rub off some unnecessary part of this solution. Since B inverse belongs to H, okay, instead of these things, we after this line we write suppose B inverse is equal to A, then which implies B is equal to A contradiction. Okay, so B inverse is not equal to A, then this is not needed. Now AB belongs to H. Okay, now I think it will look good. By the cancellation laws, we have AB not equal to A and AB not equal to B, and also because neither A nor B is a unit, sorry, what the hell am I saying, is not identity. A is not identity, here also B is not identity. So we are left with only one choice, so we must have AB equal to identity, but then B inverse must be equal to A, which we have shown here is not possible. Is not possible. So that means this supposition from where everything started is wrong. So our supposition A square equal to E is wrong, since we also have, that means A square is not equal to E, since we also have A square not equal to A, the three distinct elements of H are identity A and A square. That is, H is this, which is a cyclic subgroup generated by A. That's how we have shown that any subgroup of G of order 3 must be a cyclic subgroup generated by some element. Okay, now it is given that in our group there are exactly 8 elements of order 3. Let the elements of order 3 in G be A1, A2, etc. A8, since the order of the inverses of these elements orders of the inverses of these elements are also equal to 3. They will be the same as the order of the original elements. These inverses are nothing but the original elements in some order, maybe permuted. In some order. So the elements of G of order 3 are A1 and its inverse, A2 and its inverse. Without loss of generality, we are assuming that these are the elements. A3 and its inverse and A4 and its inverse. It may not be the case that in this order in which you are seeing the elements here actually give you these distinct elements, but of course we will find such pairs of an element and its inverse, and we can rearrange them if we need. So here we write without loss of generality. So that means these are the only available elements of order 3, and each one of them will generate a cyclic subgroup of order 3. The thing is that the cyclic subgroups generated by A1 and A1 inverse will be the same. Clearly, just like that, the one generated by A2 and A2 inverse will be the same, and so on. And also, since we have already proved that any subgroup of G of order 3 must be a cyclic subgroup generated by some element, and as a consequence that element must be of order 3 itself, so that element must be one of these elements. Hence, taking everything into consideration, the cyclic subgroups of G of order 3 are precisely these: A1, and so G has exactly 4 cyclic subgroups of order 3. So this completes the solution. I planned to solve some more exercises, but I think I lost a lot of time in this solution because I got confused. Anyway, so we will let us just stop the video here, end the video here, and we will continue in the next part. Hopefully we will be able to complete this set of exercises in the next part. So that will be all in exercises of Gallian in this video. So see you in the next part. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.